Okay, so today we're going to start the first lecture, which is units, physical quantities, and vectors. That's chapter number 1. Today we're just finishing the first part. Next week we'll finish the other part of chapter number 1. Now we have objectives for this lecture, and our objective introduced the international system, which we call SI units, and then define 3 fundamental quantities of mechanics, express the physical quantities in SI units, to keep a track of significant figures in calculation. Now, as you see in the first slide here, the nature of physics is experimental. Okay, we make observations and we try to understand these observations. What are the basic laws or principles underlie this behavior that we see? So usually we try to look for a physical law or a principle to explain what we see in observation. So for example, you have what we call the gravitational law here, and you all know about Newton. Before Newton, human notes that if you release any object, the object falls toward the surface of the earth. Now, usually if you want to move things, you have to apply a force. Either you have to pull or push onto them. But this basically is just falling in itself. They don't see any force. And that's why they call this free fall. They don't see anything affecting it. It falls on itself. Then Newton said, well, because of what? Because of gravity. And he went on to explain why the planets are orbiting the sun. Before that, people say there is something that forces these planets to orbit the sun, but they did not know the reason. So Newton basically said if you take 2 objects, let's say mass 1 and mass 2, you separate them by distance r. Well, there is a force between both of them, which is G m1 m2 over r squared. And he said that's exactly what's happening between any object and the earth itself. And that's why objects are pulled toward the earth, because the earth has a bigger mass. And of course, that's why the planets are orbiting. If you take the sun and you look at the earth is basically orbiting the sun because of the gravitation between the earth and the sun. So these are the things that we look for in physics. We look for physical law to explain a model, to explain what we see, or a principle, okay, something that underlies the why the objects are behaving the way they are. Now, in this course, you will learn concepts in physics, principles, and then physical laws. And then you apply these to problems, how to solve problems. So there is a strategy here in solving problems in this course or in physics. And we put something here, what we call IC. I here coming from identify. That means first you're going to identify your problem. What quantities you are given and what quantities you're required to obtain. The second is to set up the problem. You have your physical laws and so on. So the way you set up the problem, you're going to set up equations and so on, and then you're going to execute. And finally, you're going to evaluate. Your answers make sense, don't make sense, and so on. And that's why the abbreviation here of IC. So that's the strategy that we're going to follow. And what we hope for is to explain concept and find out principles and physical laws. Now, as I stated earlier, that basically physics is an experimental science where you make observation. And when you want to make this observation, you basically want to quantify them. So you look at them and you look at them again. So you're measuring them. So how do you measure them? You need tools. Well, if you need these tools, that you need standard. That means you can repeat these things, or you make sure, or you see any changes into them. Through history, many civilizations, they use different units for measuring things. Now we try to come up with a standard way that scientists use in their way, but we have to agree on the quantities that we're basically measuring. So in physics, there are three basic quantities, which is length. And length basically measures distance, okay, locations, areas, volumes, okay. You want to see how big, how small, and so on things are. And then mass, which is basically how heavy. And time. Things change in time. So these are what we call the basic quantities. And sometimes we give these dimensions. And I don't want you to, in this case, I don't want you to confuse these dimensions with 1D or 2D or 3D in space. You're only measuring length in that situation. But length here will be given a dimension of length. Mass will be given a dimension of mass, and time will be given a dimension of time. And the reason for that, different places or different countries can use different units in measurements. And if you don't know what that unit is, you can ask, this is a unit of what? So if they tell you a length, that means it's for length. Mass, then it's measuring how heavy or how light. Time, then you know it's for time. And that's why we call these dimensions here. And these are the three basic quantities. You can build other quantities out of these. So for example, I'm sure that in high school you saw speed, force, acceleration, and energy. And these will have dimensions of their own as well. But you can derive them from these basics. So for example, probably in school you studied that the force should equal to MA. So the dimensions of this force must have the dimension of mass multiplied by the dimension of acceleration. And you know that if you look at the dimension of acceleration, it will be length over t squared. It is length divided by time squared. So you can always derive these from these three basic quantities. Now, so you will have units to measure these. And as I told you, through history, you have different civilizations that use different units and so on. Now, the world is communicating with each other. We want to do science, so we want things to be standardized. So we're going to use a standardized system, okay, for measurement. And this was agreed on in France, and this is called the international system. However, it was done in France, and the French language is different from the English language. So instead of saying the international system, they say system international, and that's why it's abbreviated as SI. Here with United Arab Emirates, we say UAE. We take the abbreviation here. So the same thing here. It's abbreviated as SI. And some people say it should be IS. No, it's coming from the French. And where we call that this is the SI units. Now in this, the standard for the SI units was meter for length, kilogram for mass, and second for time. And this is sometimes known as the MKS. That means meter, kilogram, second as well. You may also hear something that called a GS. And C here stands for centimeter, and G here stands for gram, and S for second. That means if you're using these units. But the SI system is basically using the meter, kilogram, and seconds. Now there are other systems like what's used in the US or used in the British system. They use feet for length, seconds for time, and slugs for mass. And if you are not familiar with these units, you can always ask the question, these are units of what? So we'll say slugs are units of mass. Then you know they're talking about mass. You don't confuse it with other dimensions. And that's why we said length, mass, and time. So you can always ask the question, this unit measures what? Or it's a measure of what? And right away, if they tell you length, you know it has to do with length or mass or time. So now this is the international system, or what we call the SI system of units. Now we want to have a standard for these systems. And when the system started, when it came to measuring length, they used a bar of metal, and this was basically as the 1 meter. And you know that temperature and pressure can affect the expansion and contraction of metals. So in the standard PRO, they basically keep this under standard conditions. Okay. But that was the 1 meter. So now if you want to make any measuring tool, it has to be calibrated to this 1 meter. And of course, in every country, they start basically making their own Bureau of Standards, and they may keep standards there, but you have to calibrate against them. But scientists start looking for something more fundamental, something that you can see in nature. Okay. And you want to calibrate against that. So now, when we know that the speed of light is the highest speed that we have in our universe, and it's 2,997,92458 meters per second. That's the speed of light. So the meter is defined as the distance it traveled in 1 over the speed of light in seconds. So it's something fundamental now, but has to be done in vacuum. So if you have a laser and so on, and you have a vacuum, if you can measure it to this precise, then you have something more fundamental and more accurate. Okay. When it came to measuring the mass, they use a block which is defined as 1 kilogram, and it was kept at the Bureau in France. the International Bureau of Standards in France, kept under standard conditions. Okay. And that was known as the 1 kilogram. But it's still an object, human-made object. We want something more fundamental. I think in the past 5 years or so, we came to something more fundamental, which we call Planck constant, which is very small, but this is fundamental. Okay. So there is a fundamental unit as well that is now used for measuring the mass, but it's still measured in kilograms. So we have to convert it to kilograms. And when it came to time, you know, time from old civilization, they noticed that we have day and night, so that's one day. Then they divided the day from the sunrise to sunset. Then they start basically noticing the sun at different position during the day. So they divided the day in 12 parts. So 12 hours. They did that also for the night. So you have 24 divisions for the day, and that's why it came as 24 hours in a day, and day is basically sunrise to sunrise. And when they looked at the moon, they start basically seeing that the moon repeats its cycles approximately every 30 days. So the month is 30 days. And then they have seasons, and they notice how the sun height is different during these seasons. And they found that the season will repeat itself every 12 months, because they can basically mark the month by the moon. So we have a year, which is 12 months, and the month is 30 days, and the day is 24 hours. Okay. They came to smaller units as well, and they divided the hour into 60 minutes, and the 60 system is used by the Babylonians. And then they divided the minute into 60 seconds. But then stopped after that. Now, when we look at a millisecond, we say, when we look at a second, we say it's 1,000 milliseconds. So we use the 60 based only up to the second and so on. So how to measure that second? You make tools to do that. And of course, it will be different from one civilization to the next. And we need something standard. So when mechanical clocks were used, like the one that depends on pendulums, and then the ones that basically start using springs and so on, we try to make it more and more accurate. Now there is something more fundamental, which is the cesium atom. It has radiation, and it oscillates in time. So they use this as the standard for time. So we used to use object as a standard for these units of length or mass or time, but now we use something that's more fundamental, something that can be found anywhere, in any place, and they can basically use that as a standard for length, mass, and time to calibrate against. Any questions so far? Any questions so far? So now you want to come with a system of measurements. So if we take just length, for example, when you talk about length, we said, well, we are going to go with 1 meter. But can we have something which is bigger than a meter? Something that's smaller than a meter? So yes, the meter actually equals 100 centimeters. The meter also equals 1,000 millimeters. 1 meter also equal 1 million micron, and the 1 meter it's also equal to 1 billion nanometers, and you can go smaller, and you can also go higher. You can say 1 kilometer is equal to 1,000 meters, and so on. You can go mega and giga and so on. And this is what we call prefixes here. So you can have smaller division, bigger divisions, and so on of these units. But still, the standard is meter for length, kilogram for mass, and seconds for time. And then you can have units that are bigger or smaller, but based on these three standard units. Okay. Now, you will be dealing with equations, you will be measuring things, and sometimes you have to multiply, divide, add, and so on. So how are you going to make sure that you're doing this in the correct way? So we're going to look at something that we call here consistency and conversion. So in order for you to be consistent, and you have an equation, well, each part of your equation has to have the same units. It cannot be different units. So for example, you can measure things in kilogram, and you can measure things in a gram. But if you want to add them, you either make this in grams or you make this into kilograms. So for example, you're familiar with when you go and they measure your height, and you can say a medium height of 1.7 meters, or you can say 170 centimeters. So you always have to use the right units in your equations, and you have to convert and make sure that you basically have the right units, either in multiplication or division or addition and subtraction as well. You really have to be careful that you're using the same units and you'll be consistent. That means you have to convert if you have different units. We have an example here. You have 50 kilometers per hour, and you want to convert this into meters per second. So 50 kilometers per hour, you know that in a kilometer you have 1,000 meters. So the kilometer here will cancel the kilometer here. Now in 1 hour, you have 60 minutes, and then you have 60 seconds. So 60 times 60, it will give you 3,600 seconds. So if you take 1,000 divided by 360, that would give you 1 over 3.6. So usually when you want to convert something from kilometers per hour to meters per second, you just divide by 3.6. And kilometers always 1,000 meters. So here you have 13.9 meters per second. So if someone tells you 50 equals 13.9, that's not right. That's wrong. But if you say 50 kilometers per hour equals 13.9 meters per second, then that's correct. Even though the numbers are different, but when you use different units, then they're equivalent. So 50 is not equal to 13.9, but 50 kilometers per hour is equal to 13.9 meters per second when you use different units. So when you have equations and you want to deal with adding, subtracting, multiplying, and so on, you really have to be consistent with the units, and this means you may have to convert your units. Here it brings in another question, because sometimes you measure things, and when you measure things, you're using tools. And when you're using tools, how accurate are these tools? Or how certain? And up to what? And this is bringing in the question of significant figures. And significant figures here meaning meaningful digits in the measurements, that they have some meaning. So for example, you take the first ruler here and you measure, and you will find that you have a centimeter, and between 2 centimeters you will find 10 divisions, and the smallest division here is a millimeter. So the accuracy in this measuring tool is 1 millimeter. So when you measure, you will find, for example, it's equal to 8 centimeters plus 8 millimeters, which is 0.8. So it is 2.8 centimeters. You cannot go smaller than this. There is another measuring tool here, and this measuring tool here gives you a division between the millimeters. So it's more accurate. So when you measure, you will find out that yes, you have 2 centimeters and 8 millimeters, and also you have 5 divisions between 2 millimeters. So now your measurement here is 2.85 centimeters. Now this part here, 5, has a meaning in you because you're measuring this, but you cannot put it there because in this case it has no meaning because you don't measure this here. So in these measuring tools, okay, what is significant? Significant is something that has meaning and you can measure. So if you put 5 here, it has no meaning because you cannot measure it. But when you put it here, it has a meaning because you can measure it. And with this one, you are more certain. You have certainty. That means you have more significant figures. And of course, when you do measurements, you're going to multiply and divide and add and subtract. So how are you going to deal with these significant figures? So these significant figures have to have a meaning. So for example, if you just look at the dirham, when we're talking about the dirham has 100 fils. Now, if you go and buy anything from any store, they will deal up to 1 fils. So they will say it is 15.25. They can deal with this. Below this, they cannot deal with it. So they cannot write anything here. And if you buy anything from the stores, they always go to the second decimal place here. That's what has meaning to them. Now in banks, they can go to the third one, depending on, but that's a unit that they created. It's not physical, but these are the physical units and how you measure them. That's when you do measurements. Does the figure have a meaning? And that's what we call a significant figure. Is this clear? Any questions so far? So now, what are these rules for significant figures? How do we basically consider them? So we put some rules here. And the first rule here, we say non-zero integers are counted as significant figures. Okay? So for example, if you look at this number here, 1457, you have 4 significant figures here. At 23.3, it has 3 significant figures because each integer here is counted as a significant figure. So any integer can be counted as a significant figure. Second rule, when it comes to zeros, if the zeros are leading zeros, then you don't count them. So for example, here you have 0.0025. Now these zeros have no meaning. So the only figures that have meaning here is basically the 25. And we say here it is 2 significant figures. For example, you can have something like this, okay, where you may have 3 divisions and you want to write numbers. So if I want to write 1, I will put 0 here, and then 1. But the number is only 1. These 2 zeros have no meaning. But let's say if I want to write 10, then I will put 0 here, and 1 here, and 0 here. So the leading 0 here has no meaning. So that's one thing that you have to be careful with. Okay. And later on, I'll tell you about trailing zeros as well. Okay. So when you look at leading zeros, you don't consider them. So in this case, they're all zeros here, so we have 2 significant figures. Then we have what we call captive zeros. You put a decimal point, so you see 2 zeros. Now they have a meaning here, because I am looking at this last one, and it's a significant figure. So in this case, I count them, and I say I have 4 significant figures. And then we have here a trailing zeros. So the trailing zeros, it has no meaning unless you put a decimal point. So for example, when we say here 100, that means I may be measuring things in hundreds, 100, 200, 300, 400. The only thing that has a meaning is the first digit. Okay. And that's why we say it has 1 significant figure. But if you put a decimal point, then they are important. And in this case, you have 3 significant figures. And in this case, you put a 0 after the decimal, which means that it's important now for you. And that's 4 significant figures. Unlike this situation here, where there is no integer here. So it's not captive. So these leading zeros have no meaning. So you only have 2 significant figures. But in this situation here, you have a decimal point, and then you have, in this case, you're saying that this one here has a meaning. Like if you want to write 100 in terms of money, you will say 100.00. You're telling me that there is a filth as well that we can count. So in this case, we say that this has 5 significant figures. Is this clear? These rules are clear? Now, we'll go to the obvious that we're going to do with our numbers. We're going to multiply them, we're going to divide them, and you're going to be measuring different things using different tools. Okay, so how accurate it is. So you have one tool that is very accurate, you have another tool that's not accurate. Well, you cannot give me your result based on your accurate tool. You're going to give me your result based on the least accurate tool. So there are rules. When you multiply and divide, your answer has to come in accordance with the number of least significant figures. So look at the first one here. How many significant figures do we have here for this one here? How many significant? 3. And for the second one? 2. And for this one here? 4. So now, this is the number with least significant figures. My result has to be up to 2 significant figures. So when you do your multiplication here, it will give you 0.42. Someone will say, I only have 1 decimal place here after the 2. In multiplication or division, you look at the result has to be with the significant numbers, the least with the significant, and here there are 2. So the answer here comes as 0.42. Now for this one here, you look at this one, and this one has 6 significant figures. This one has 3 significant figures, so your answer has to come with 3 significant figures, and that's why we have 5.45. And of course, you multiply 10 to the 7 times 10 to the minus 3, and that will give you 10 to the 4. The exponents here is different, but the number that I'm interested in. So in the case of multiplication or division, your number has to be in accordance, or your answer has to be in accordance with the number with the least significant figures. In the case of addition or subtraction, then you have to look at the after the decimal point. What do you have after the decimal point? Here you have 3, here you have 1, and here you have 2. Well, your answer has to be with the one with the least decimal places. So your answer has to be up to 1 decimal place here, and that's why it's 0.6. That's in the case of addition and subtraction. Is this clear? Is this clear? So let's deal with some multiplication and divisions here. Okay, you have the first one here. If you do that in your calculation, that's what you're going to get. So this one here has 4 significant figures. This one has 3 significant figures. Your calculator will give you 6 significant figures. But that's not the right answer. The right answer has to be up to the one with the least significant figures, which is 3, and that's why here you have 49.7. You may actually say I have 2 decimal places here, but I'm interested in the number of significant figures, and that's why you have here 49.7. The same situation here. You have the 3 significant figures. Here you don't count the 0. You will have 4 significant figures. You do, that's what you get out of your calculator, but your answer has to be only 3 significant figures. The same situation here. You have 4 significant figures. Here you don't count this 0, but you count this 0 here. So here you have 6 significant figures. That's your answer. So your answer has to be 4 significant figures, and that's why we don't count the 0, but we count the 4 significant figures. Similarly here, you have 10 raised to the 6 multiplied by this. So you look at that, this is 4 significant figures. So your number has to be 4 significant figures. So if you multiply that, you may actually get, if you do that, it will give you 15 point. So you want to make sure that you get the right significant figures. So you shift that one decimal. So it will be 1.586 times 10 to the 7. To get more accuracy here. Now this number here that we have, this 4, and this is 4, you have 10 to the raised to 23, you have 10 raised to the power minus 24, you actually get here 1.000, but the answer should be only 4 significant figures, and that's why you have 1 point and 3 zeros after the decimal, to make sure that we have 4 significant figures. So these are the rules with these meaningful digits that we have that comes out of our measurements. When you divide or subtract, the answer has to be in accordance with the number with the least significant figures. If you add and subtract, you look next to the decimal place, and of course it has to be the one with the least decimal places. Is this clear? Any question on these? So we have here, we ask questions So if I ask you about the first one here, how many significant figures do I have in this number here? 4. Now I ask you here, how many significant figures do we have here? 3, because the leading zeros are not counted. But if you come to this one, how many significant figures do we have here? You will have now 5, because you're going to add them. Okay. Now here you will have 4. Here you will have 5. Okay. And that's how you basically consider significant figures. And they have meaning. And I told you it comes from the measurement. Okay. So for example, if you have money with you and they ask you to pay them, okay, the money that you owe to the store, he will just tell you whatever, let's say 100 dirhams and 59 fils or 60 fils. He cannot go 600 fils because you only have 100 fils in a dirham. It has the third place after the decimal has no meaning when we try to deal with dirhams here, unless you go to the banking and they make another unit there. But physically, it doesn't exist. So when you measure things, that's basically the meaningful digits are, and which we call a significant figure, and they, of course, will come in calculation, and the calculation has to reflect the accuracy in our measurements. Is this clear? Is this clear? Now, once you do that, of course, you can also make conversions. Okay, you want to convert your units. Okay, so for example, they give you here a official record land speed, which is in miles per hour. It's 1,228 miles per hour. They want this to be in meters per second. And they tell you here that 1 mile equals 1,609 meters. So you're going to multiply this by 1,609 meters. And of course, to convert hours into seconds, it's 60 times 60. 60 minutes times 60 seconds, which is 3,600 seconds. And it will give you 548.8 meters per second. So 1,228 is not equal to 548.8. But if you say 1,228 miles per hour equals 548.8 meters per second, then that's okay. When you include what? When you include the units. Here they give you something which is given in a cubic inches. I wanted to convert this into cubic centimeters and cubic meters. You know that 1 inch is equal to 2.54 centimeters. So to do that, you're going to convert the inch in 2.54 and cubic, that means inch times inch times inch. So it's 2.54 raised to the power 3, and you get this answer in terms of centimeters. And of course, you have to watch out for significant figures. Your answer has to be 3 significant figures, and that's why you have 3 significant figures here. The same thing if you want to convert that into meters. You know that a centimeter is 1 over 100, which is a meter, which is 10 raised to the power minus 2 meters. So if you do that, it will be 10 raised to the power minus 2 raised to the power 3, and you get 30.2 times 10 to the minus 6 meter cube. So you have to make these conversions, especially if you're dealing with equations and you want to do calculations and so on. Your units have to be what? Have to be consistent. Now, Here are just examples of how to look at these. So for example, you're adding here, and when you add, you only have one decimal place here. Okay. But now you're multiplying, and this is 3 significant figures. So your answer has to be 3 significant figures, and that's why you have 176 here with no decimal places. The rules are you need the number of significant figures. So it has to be 3. Now here, 12 times 34 times 9.45 millimeters. So can you do that in your calculator? Can you multiply this number out and tell me what the number is? 12 times 34 times 9.445. Any answers yet? Well, the answer here is 3853.56. Okay. Now you need your answer to be how many significant figures? How many significant figures? You said that the answer here is 3853.56. Now, how many significant figures do you want this answer to be? 2. So if it's 2, you will say 38. Is this a reasonable answer? No. So how do you handle that? Okay. Well, you will say that it's 3.9 times 10 to the 3. So you have the right number of significant figures, but you're not losing the other order of magnitude. So that's how you write it. Is this clear now? Okay. You see? So you keep with the number of significant figures, but you can basically raise things to the power when you are in a situation like this. Now here you need 1 significant figure. That's why you have this. Here in this case you need 3 significant figures, 2 significant figures, because you have 550 and 0 here is trailing 0, so it's not counted. So you only need 2 significant figures, and that's why you have the answer here. Okay. When you add things, you only have 1 decimal place here, so your answer has to be to 1 decimal place, even though you have more accuracy here, but one of your instrument is less accurate, so you end up with 1 decimal place. The same thing here, you have 1 decimal, here you have 2, but it has to be only 1 decimal, your answer 1 decimal place, and so on. Okay. So that's basically how you deal with significant figures when it comes to multiplication, addition, and I told you these significant figures have meaning. They come out of your measuring tools. So in this lecture here, we define standards for the SI units. We can convert units to SI units, okay, or to any other units. Just make sure that your equations are correct. And then we talked about significant figures and how to use these significant figures. And the reason we do that, because you're going to deal with equations and you are going to multiply different quantities or divide or add, and some of them may be less accurate depending on the machine. So how can you handle all of these? Is this clear? Any questions on these? Good.